last time we looked at MOSFETs without voltage applied, I believe, and how they were constructed and how they were made. And now we're going to look at what happens when we actually apply voltage. The only thing we did last time was apply a gate to source voltage, which created a channel the current could go through. But now we're actually going to talk about what happens when you apply a drain to source voltage once you've got the gate to source voltage set and you've got a channel that is allowing current to flow. So you've got the channel, and then what ends up happening is we start to apply a VDS voltage, and we're going to start with a really small value. So not a really huge value, but a small value to start with. So we apply a voltage, and what ends up happening is that current will flow in the opposite direction because electrons are being attracted towards the positive charge of the drain, but of course current goes the other way, so it kind of flies through there and comes out the other side. And you will notice that the source current and the drain current are exactly the same current. There's no difference between them. It's just the current goes in the drain, out source. They're exactly the same. When we get to bipolar junction transistors, that will not be the case. They will look kind of similar, but it's not the same process, so those two currents are not the same. But the drain current, the source current, they're the same, so we never talk about the source current. We generally just talk about the drain current, and we know that it's going to be the same as the other. The gate current is 0, so there is no current that flows into the gate at all, but it does provide a voltage. And once it has provided a voltage, then we can have a channel. So VDS is small, and this is like really small. And when we do that, there's actually a linear relationship with the conductance of the channel and how far above VGS you are, so how big the overdrive voltage is. So if there is no if VGS is less than the threshold voltage, doesn't matter what you do with VDS, you get nothing happening because there's no channel. So that's kind of obvious. But then as you go on and you increase VGS, so basically we are applying whatever the threshold is plus some kind of voltage, some standard voltage. And then VDS, if you turn it up and leave it kind of small, you actually have a linear relationship between the current and the voltage. And you can keep going up and get higher and higher values of VGS, and you get different slopes. And the slope of this is actually equal to the conductance of that channel, of that drain to source channel. So you can actually figure that out. Sometimes we do 1 over the resistance of the channel, but it's all kind of the same thing. And it's a direct function of whatever the overdrive voltage is. But this doesn't remain true forever. This just is really, small voltages, which if you've had 2401, you may remember that, or you may not, I don't know. But now, this is where MOSFETs get interesting. As we let VDS get larger. When we let it get larger, the channel starts to become asymmetrical. So at the source end, it actually gets deeper and bigger, but at the drain end, it kind of doesn't, and it actually begins to get a little bit smaller. So you actually end up with a tapered kind of channel. And if you keep doing that, first of all, as you let ID go, or VDS go up, you start to get a nonlinear relationship between them because now the channel is tapered, and so there's a little bit of more interaction. So it begins to become nonlinear. Eventually, you get to a point where the end of the channel closest to the drain actually closes or pinches off. And then you get a situation where it doesn't matter what you do to the drain to source voltage, you don't get more current out of it. You get the same amount. Now, what ends up being the question in here is how do you get current to keep going when you've got pinch off? Because pinch off implies that it's pinched off. And this is really just unfortunate terminology. It's described that way because the end of the channel closes, but that doesn't mean the current stops flowing. What ends up happening is electrons from the source end, remember the electrons are coming from the source to the drain. They're going opposite to the direction of the current. So what happens is the electrons move through and then they're swept across that bit of depletion region to get to the other side. So electrons keep going. They keep moving. They go into the channel at the large end, and then they just travel, but because there's a positive charge at the other end, they just get pulled across the depletion region and out to the other side. So you can't make it bigger. You can't make more current once you've gotten to this point, but current will still flow. And that's one of those things when I was a student, nobody ever explained to me. They just said, oh, you get to pinch off, the current's constant. And I'm thinking in my mind, well, if it's pinched off, why is there current? So it took me many, many years to actually sit down and figure out how that worked. But current keeps flowing, it just can't get any larger. So it kind of stabilizes and gets, well, it reaches its maximum value for that particular value of VGS. And this is sort of a summary of what I just said. This is what always happens to me. So, yes, so what we get is actually the saturation current. So when we get to the point where this current can't be increased anymore, where you turn VDS up and you just get a constant current, that is the saturation current. And the point for VDS where that occurs is the saturation value of VDS, or the minimum value of VDS you need to be in that constant current region, because the constant current region is actually where a lot of the operation takes place. So there are two areas in which MOSFETs operate. If VDS is greater than the overdrive voltage, remember the overdrive voltage is just VGS minus the threshold voltage. If it's bigger than that, it's in what we call the saturation region, which means the current is saturated and basically constant. If VDS is less than the overdrive voltage, it's in something called the triode region. And the triode region is where there's a more or less linear relationship between VDS and ID. It's not quite completely linear all the time, but at least it does affect those values. So if we look at this graphically, there are two distinct regions of operation. We have right at the bottom where 0 is, where there's an almost linear relationship between VDS and ID, which means that the value of VDS, if we come up with an equation to describe that, I'm not going to derive, but I am going to tell you what it is, VDS will appear in that equation because it actually affects that curve. And as it moves up in VDS values, the curve starts to bend because VDS getting higher is starting to increase the resistance, the channel is starting to change, and then the current ends up saturating due to the pinch off at the drain end. So VDS then doesn't affect the current at all. We just have values of VDS, and that line just remains, as you'll see later, not actually constant, but close to constant. So two areas of operation, saturation and triode. Should I warn you now? Mm-hmm. I'm going to warn you now. When we get to talking about bipolar junction transistors, there's going to be a very similar curve, but the area where it's marked triode is called saturation, and the area that's marked saturation is called active. So what this means, MOSFETs, saturation is where we want to be if we want to build an amplifier. A BJT, saturation is not where we want to be to build an amplifier. But I'm just warning you, I'll mention that again later. But saturation means something different for bipolar junction transistors than it does for MOSFETs. Yes?
Both of those inequalities have equals in them. Should we just assume when it's equal it's saturated?
That's the actual VDS saturation value. So it's actually so rare that you get to that exact line. That it could be one could be greater than and not equal, but the equal value is actually where just the junction is. And that doesn't really tend to affect the operation that much. Nobody ever operates right on that line. You operate way above or way below. So the drain current saturates when VDS equals the overdrive voltage, which technically, yes, for that sign I should have had plus, greater than, and less than, and no equal, but whatever, I don't care. You shouldn't either. So when we want to quantify this, since we have a relationship between the overdrive voltage and the drain current, but we don't have a relationship, we don't actually care what VDS saturation is, we actually can quantify the drain current by just taking this constant at the front, which I will explain in a minute. Width over length, we've talked about where the width and the length is in a MOSFET. The width is going back into the page. The length is the distance between the two heavily doped channels. And the more standard way of representing, sometimes we use VOV for simplicity's sake. Say if we're trying to find that value or find VGS, we might use the overdrive voltage to solve and then go ahead and add on the threshold voltage in order to get that value. But the standard equation that's used is this one here, where we have Kn prime, which I'm going to explain in a second, over 2 times the width and length ratio times the difference between VGS and V threshold squared. And that's what gives you that kind of parabolic effect and why it ends up looking a little parabolic. So the question is, what is the value of Kn? That is known as the process transconductance parameter. And that is just a combination of the mobility of the electrons and the capacitance of the gate. We talked a little bit about the capacitance of the gate last time. And if you multiply them together, that's what you get. You get this process transconductance parameter. And the mobility of the electrons is a standard value that's generally figured out, and oftentimes you're just given the Kn prime value and don't worry so much about the individual mobilities and capacitances, but you could if you wanted to. Yes, yes. So just to give you a short example. Oh, okay. Oh, well, I'm not even going to worry about that. Let's say we have a semiconductor process and it has specifications. We have length, we have the thickness of the oxide, we have the mobility of the electrons, and we have the threshold voltage. And you will notice that the mobility of the electrons is actually in centimeters squared per volt seconds, which we will address in a second. So we want to find the capacitance of the oxide and then the process transconductance parameter. So the value of the capacitance is equal to the permittivity of the oxide, and that's a constant. That's always going to be the same. It's going to be 3.45 times 10 to the minus 11. And then we divide by the thickness, and the top and the bottom are both in meters, or, well, they'll come out in farads per square meter, but the base unit for both is meters, which is why we used 8 times 10 to the minus 9. So we get 4.32 times 10 to the minus 3 farads per meter squared. And if we wanted to, we could simplify that and put it in femtofarads per square micrometer. But for the next part, we're actually going to use the farads per square meter part to go ahead and fix that. So we're going to use 450 times 10 to the minus 4 for the mobility of the electrons, because we're going to change that into meters squared per volt second rather than centimeters squared per volt second, which makes it easier than try to convert it to micrometer squared. That's actually ends up with large exponents for both, and so Putting it meters squared is a little easier. So we get 194 times 10 to the minus 6 amps per volt squared, and we can change that to 194 microamps per volt squared. And that's a pretty typical value. The process parameter is generally rather small. I could think of something to say while people are writing, but I'm too tired for that. I'm just enjoying the rest. So, now that we have that, we've made a MOSFET out of it, and we have a width-length ratio of 8 micrometers per 0.8 micrometers, and we're going to use the process transconductance parameter from the first part and find the overdrive voltage, VGS and VDS minimum needed to operate in the saturation region with the ID equals to 1 microamp. So because we're looking for the overdrive voltage, we're just going to use the equation that helps us solve for that rather than splitting it up into VGS minus V threshold. We'll split it up in a minute. And if we move that around a little bit, we get the overdrive voltage is the square root of ID times 2L over Kn prime W. And then we can put in all the numbers. We have 100 times 10 to the minus 6 for the drain current. We have 2. We have 0.8 for the length and 8 for the width, and then the process parameter we found before. And I didn't worry about the fact that both of those values were in micrometers because they cancel. So we just used the numbers and didn't worry about what the actual units for that were. And we get 0.32 volts. And all I'm going to do is kind of move that up a little bit so it's still there. And we will find VGS. VGS is just the threshold voltage plus the overdrive voltage, so we just add the 0.7 from the first part of the problem to 0.32, and we get 1.02 volts. And VDS minimum is just going to be the overdrive voltage, so that's 0.32 volts needed to operate with ID as 100 microamps. So that's not overwhelmingly awful, just is. So P-channel MOSFETs, which we don't use as much in here, but we do kind of talk about, they're constructed pretty much the same way as N-channel MOSFETs. The only difference is the P and N areas are switched. So when we actually apply voltages, everything is in the opposite polarity in the opposite direction. So current goes into the source from the source to the drain. And when we apply VDS, you can see that the polarity of both the batteries is actually switched for VGS and VDS. So sometimes we call it VSG and VSD just to reverse the polarity. Otherwise, it would be like a negative number, and that would be fine. So either way, like I said, we don't deal with those as much. Yes?
What are the different application purposes for?
I'll show you in a minute why we have PMOS, because there are some disadvantages to PMOS, which I'm going to get to. We do have a process transconductance parameter the same way, but you'll notice that there is the mobility of the holes. The mobility of the holes is different. It's actually smaller because electrons, when they're moving and when they're carrying charge, are moving in the conduction band of the structure, and they're a little more free to move. Holes are actually move because electrons are moving to adjacent holes, and the holes kind of have a net movement. but that's a different movement for an electron. So both the mobilities are actually dealing with electron mobilities, but the mobilities of the holes are smaller than the mobilities of the electrons. Generally, a quarter to a half the mobility. So PMOS devices actually have to be bigger. They have to have a width to length ratio to get the same effect. So they can have a disadvantage in that respect. But this is what they're good for. The thing that they're really good for is when we combine them both together, the PMOS and the NMOS, which I'm not going to go into where the current goes and all this stuff because that would be a bit complicated, but putting NMOS and PMOS together makes what we call CMOS. And CMOS appears in a lot of circuits and is actually replacing a lot of bipolar junction-based circuits because it works well with logic and with analog circuits. So this is actually one of the bigger applications of PMOS, is combining it with NMOS so that we have this complementary MOS kind of circuit. And the N well on the PMOS side is basically made because you've got a P plus and a P type, and it's kind of getting pulled, the electrons are kind of getting pulled out of there. But in any case, we only cover that to let you know what it is. And then you do have a lab where you kind of simulate this. We don't actually have one for you in your lab kit, but there is a simulation that you do after, not next week, not the week after, but the week after that, whenever that is. There is one to do. So circuit symbols for each are just basically with arrows telling you which way the current is going. So with PMOS, the current is kind of shown as coming out of the drain, and in NMOS, it's shown as coming into the source. And those look like they're doing the same thing, but they're kind of not. The other thing is that sometimes there will be a fourth connector, which is the body or the bulk electrode or whatever, and the MOS devices you have that connected on the inside, so you don't have a terminal to deal with that. But with some, you might see a fourth terminal, and that would just be the body terminal. And most of the time, that's just connected to the source in the circuit. But sometimes it's not, depending on what the application is. So a summary of the characteristics and how the equations work is here. I didn't go through kind of how we get the equation for ID in the triode region, but you can see that there's kind of a square relationship where you have VDS and VDS squared, and it affects heavily the value of ID in the triode region. That's where you have a channel that's open all the time. The value of VDS does affect the drain current, and then VDS is always going to be less than the overdrive voltage. In the saturation region, you'll notice that the ID equation does not include VDS anywhere because it doesn't depend on VDS anymore. It depends on the value of VGS and the threshold voltage. You'll also notice that we differentiate, once we start talking about actual NMOS, we differentiate the threshold voltage for the N channel. We actually have one for the P channel too. So if you see a T and then an N, that just means we have an N channel device. It's not different than the threshold voltage from earlier. It's just denoted a little bit differently. So looking at that graphically, if you look at all the several different values of VGS, you can see that for higher values of VGS, you get more curving, and then you get a flattening out and a higher current. The value of ID depends on what the overdrive voltage is, and there's a kind of a delineating curve that travels up and shows you where the different sides are. So the triode region actually has a curve separating it from the saturation region, and that curve is actually described by the red equation above it. So you can actually find that curve and plot it. Not that we would ever do that in here, but one could. And that's the point where VDS is equal to the overdrive voltage. And so it's going to be different for each value of VGS. So we end up with kind of a a graphic that describes everything almost that goes on with an NMOS. So what we can do is we can actually model this if we have large signals, which large signals means you're applying something that's changing a lot. We can actually model this as a voltage-controlled current source. And when we do that, you see we have a current source that is directly related to VGS. So if VGS goes up or down, the value of that current on the other side will be changed. But you notice VDS is an output voltage which really doesn't look like it's attached to anything. It's just there. There's nothing for it to be across, and that's because in the saturation region, VDS is set by whatever value we happen to end up with. So it can change, but the current is going to depend directly on the voltage. So we can change VGS, that will change the current. It will actually not, the voltage, the output could be whatever, it doesn't matter. So that's a kind of reasonable model. The problem is it's not complete. There is one other part that has to be added to it to make it actually complete. Because if you go and actually if you're able to take a MOSFET and create characteristic curves, which is hard to do because MOSFETs get hot, and when they get hot, they stop doing what you want them to do at all. And I think in lab you do kind of make characteristic curves, but they just look like lines at a couple different places because it's not as easy as doing this like for a bipolar junction transistor. You can get the characteristic curves by hand, and it's not that difficult to do. With a MOSFET, depending on the MOSFET you have, it's much more difficult. And basically what you have to do is pulse the voltage. So you have to pulse values of voltage, read the current, and then lower it all and let it cool down and then do it again. So it's an automated process. If you can automate it, which people who know how to do LabVIEW can do, then you can actually get characteristic curves, but it's not easy. So this is what actually ends up happening. The common source curves, and I'm going to describe what that means. Those were the curves we were looking at. These are what we call common source curves. We're calling them common source because the source is common to the input VGS and the output VDS. So you notice both of them have source in it, which means the source is common to both input and output. And that's what common whatever means. And we'll use that a lot in amplifiers and transistor amplifiers a lot. We're going to have one terminal that's going to be common to the input and the output. Common source is the most common one that you see with MOSFETs. But when you get to a point with a real MOSFET, you don't actually get absolutely horizontal curves in the saturation region. Because as VDS goes up, the pinched off channel actually starts to get shorter. It gets shorter because there's an increase in the electric field. So there is actually an increase in the drain current. It's not huge, but it does actually drift up as you go, which you know, be real. Of course it's going to have an effect somehow, and it does. So what they call this shortening of the channel, is something called the channel length modulation. Since modulation kind of means change, but the channel length changes. It's a function of VDS, and it actually changes the equation for ID slightly. Frequently, we will assume that this lambda value is 0. When it's 0, we go back to the original equation. And when we start analyzing DC circuits, pretty much all the time we will say, look, lambda's 0. But for this week, it's not 0. For other weeks, it might be. So we do have to take that into account. And we can actually find the resistance of the slope of that curve if we take the partial derivative of that equation. So of the new updated ID equation, we can actually take the partial derivative and figure out how to figure out what that resistance is at the output. So the first thing I'm going to do, I'm going to give you two equations. One is the original ID equation. That's ID prime. That's the original one we did. And then the new ID equation is the one that actually has the channel length modulation in it. And the output resistance that is a result of that is actually the inverse of the partial derivative of ID with respect to VDS, and we keep VGS constant when we do that. So what this means is all that stuff in front of 1 plus lambda VDS, that's all one big constant, because we're assuming VGS is constant. We know the process transconductance parameter is constant, the width, the length are constant, the threshold voltage is constant. So all that stuff is not included in the derivation. All we need to take the derivative of is 1 plus lambda VDS, and we need to invert it eventually. So once we do that, we get lambda, and then we actually get ID prime after that, because the 1 goes away, and lambda VDS, if you take the derivative of that, is just lambda. So we get lambda times the original ID equation, which means that to find this output resistance, we can just take 1 over lambda ID prime, and that will give us the value that we want. We could also kind of estimate that value, but, and I'll show you kind of why now that I think about it. I've been teaching this for a while, and I always talk about the estimation, and then I realize, well, actually, you know, the estimation value doesn't really make a lot of sense now that I think about it. It doesn't save you any time, and I'll tell you why. So if we look at the characteristic curves, you notice that each one of them has a different slope, so a different resistance, and we can extrapolate all of those curves back to one point. And that one point is minus some voltage. It's actually a really big voltage. It's like 100 volts. And we call it minus because it is a negative voltage, so a minus is going to give us a plus value. And that is equal to 1 over lambda, whatever lambda is. So what this means is that finding the value of R out, we can take 1 over lambda ID prime, which is the current without the channel length. That's what's our original equation. Or we could take VA over ID prime. Or if we happen to know lambda, we could take VA over the new ID. And that's going to be different. So I'm pointing this out because you can, if you use the new equation, you can estimate that value. But it actually, to me now, doesn't make any sense why you would ever want to do that, because you're actually including lambda twice, because VA is 1 over lambda, and then ID has lambda in it. So now that I've actually gone through and figured this out, I think it's dumb. So you can just do that.
Which was more accurate?
The one that says equal, not the one that says approximately equal to. So you can take VA over the old ID equation, and that will give you the exact value, because VA already takes into account lambda. So we don't need to put lambda into the equation. We can just calculate ID without it, then just use it either as part of VA or part of lambda. So I think next semester I'm just going to take that out because it's dumb. So anyway, but I had to hack through somebody else's derivation, and I realized they did it wrong. And once I did it right, I realized, well, then the estimation doesn't really make any sense. So anyway, that's neither here nor there. So what this actually boils down to is the model is a little bit different when we take that into account. And we've added a parallel resistance to that current source, which means that the actual drain current, and I suppose this is why the estimation might work. If you knew VA and you measured ID, then I guess you could actually use that. So if you had that as part of your, whatever you call it, spec sheets, you could do it that way.
From Ohm's law?
Actually, there is a way to solve this through Ohm's law, which I'll tell you about in a second. But it wouldn't be able to do it because basically this shaded box, that is the MOSFET. So you can't get inside the MOSFET and measure ID prime. You can calculate it, but you can't actually measure it. So you can measure ID, which is the drain current, and if you knew from a spec sheet what VA was, you could actually estimate that R out value, but not actually get the exact value. It's really close. When you could use Ohm's law, if you could get ID prime, you could take ID minus ID prime and multiply that by RO. Or if you know what VDS is, yeah, you can find VDS. You take VDS and divide it by ID minus ID prime, and you'll get the same number, because I tried it. So you can do that. So the output resistance makes it what it should be, but oftentimes when we model it, we leave that out because it doesn't make a huge difference. It makes a bit of a difference, but it doesn't make a huge difference. So, oh, almost done. Awesome. So I'm not going to go into the same amount of detail with PMOS. We have the same situations going on. I'm basically just going to summarize the PMOS information for you. It's almost exactly the same. The one difference is we have a KP prime instead of KN prime, and then we switch the polarities of the gate to source and the drain to source voltages because they're negative, and then we use the magnitude of both the overdrive voltage and the threshold voltage. And we do that so that when it's plotted, it's in the right quadrant. That's basically the only reason why. So when we make calculations, we generally have to use a magnitude value. And the same goes with the actual channel length modulation equation for PMOS. We can add that in, and we use the magnitude of it rather than just the actual value, because it would be a negative, 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 and we really just want the positive value.